Good morning. Welcome back to class. Hope you're feeling all refreshed and stuff after the weekend. Hope you can take like a nice deep breath now that the assignment's done and we're basically done with the math stuff in the course. The lectures from here on out are hopefully going to get a lot less confusing. This first topic will probably trip you up a bit, but nowhere near as much as that inequality stuff. And also definitely don't let your guard down because assignment 2 is going to drop soon enough, and it is actually just asymptotic notation. It's allegedly finished. I just want to give it another run through before posting it so that I can delete any obvious typos, and then hopefully any typos that remain aren't too obvious. But I'll do a little overview of it right now. While the previous assignment contained mostly math stuff and a bit of code, this one is all math. So you'll submit it only on CrowdMark. And you'll do a bunch of proofs similar to the ones done in class. So question 1 is with big O and big omega. Question 2 is sort of a more intensive proof to do with big O. Then you have big theta, little o, and little omega. All of these, by the way, are from the definitions. And then you do some stuff like what we did on Friday. You have some facts from those readings about asymptotic notation, and then you use those to do some slightly faster proofs. Question 5 concerns properties of functions for any given constants, a and b. And then question 6 generalizes it further, where f and g can be any function. And then there's an actual bonus question this time. Turns out the formal definition of a limit is quite closely connected to the definitions of these asymptotic notation things. You can see that for yourself if you take Math 2080 Intro to Analysis. You can use limits to prove certain asymptotic notation properties. This is technically part of the course material. It was in the readings last term, but I noticed that it never actually came up in any assignments or tests. So rather than add required material to your already busy schedules and an already very difficult course, I just made it a bonus. If you want, you can check out the readings and then learn how limits relate to asymptotic notation. If you don't, I don't care. You can still get 100%. If you have any questions about the assignment, just put your hand up, but I don't expect much yet because on the surface, this is quite straightforward. Once you actually get into the proofs, things will get kind of dicey, but for now, I hope it's easily understandable that this assignment focuses on asymptotic notation. Yeah.
For the last assignment, you told us which, like, 2 of them you had to prove they were true or false, and then the other ones you knew that they were automatically true.
Oh, yeah.
For these questions, are we going to know that they're automatically true, or do we have to?
Yeah. Every question on here is, or everything you have to prove is true. There will be a couple questions where you have to show that something is not in big O. So like you will have to do stuff with negating a definition and then proving the negation, but you can still rely on everything stated here to be true. Yeah?
I would like to do assignment one grade back sooner, or after this assignment is due, I'll be getting that.
Sorry, could you repeat that?
When we are getting our assignment one grade,
Oh, yeah. I'm not sure. I'm going to have to talk to the markers about this because they know their own workloads better than anyone else. But the first suggestion I'm going to make is, can you get this done by the 14th so that you guys can have your feedback back by the time this is due? I'm going to try to make that happen, but I don't want to make any guarantees because the markers are people too, with their own stuff keeping them busy. Okay, any other questions? Cool. Let's not quite talk about actual coding stuff, but get closer to that than we ever have been. Even better, for the first time ever in the course Data Structures, Analysis and Implementation, we're going to talk about data structures, kind of. Our intro to this topic is to do with a thing called an abstract data type. This idea of interface versus implementation, the writing code to implement an ADT, is very important, but kind of hard to wrap your head around. It's very likely that on this week's quiz, one of the questions will be, what's the difference between an abstract data type and a data structure? So we're going to look into that now. So an abstract data type is a collection of data together with how it's structured, how it's organized, what properties that it has, alongside the operations that can be performed on that data. And then an ADT doesn't actually exist in code, but instead when you're writing a program, you program a data structure to implement an ADT. I have no idea if this comparison will be helpful because it kind of goes more advanced than this stuff. But if you're into abstract algebra or like second year or higher linear algebra, you could kind of think of an ADT like something like a ring or a group, a field, a vector space, because those consist of a set, which is analogous to our data, and the operations that can be performed on that set or data or whatever. And then if things like rings, groups, fields, and vector spaces are ADTs, then things like integers and addition, or the real numbers addition and multiplication, would be the data structures in this metaphor. When you're doing basically anything in computer science, it's good to consider the level of abstraction you're on. All computers work in terms of like electricity and circuits and whatever, but we'd never get anything done if we focused on those. So we rely on the physicists to do their thing, and then we abstract their work into things like bits, bytes, words, and addresses, stuff you cover in Comp 2280. But even that's too complicated to work with, so we use high-level languages to, along with some reliance on the bits, bytes, words, and addresses just working. And we use things like arrays, classes, and pointers to work with them more easily. Another level of abstraction higher, the arrays, classes, and pointers all work as you expect, but you want to zoom out a bit further to solve some more interesting problems. That brings you to the abstraction level that we're working on in this course, or at least during the lectures, because you're going to be implementing these during assignments using arrays, classes, pointers, and whatever. We think of ADTs, examples of them include lists, tables, stacks, and queues. We'll go into more detail on individual ones later. And yeah, we are able to ignore details on arrays, classes, and pointers and focus on the data structures. Then finally, in the real world, eventually you'll be designing and implementing ADTs to serve a specific purpose. Cool. Those examples on the previous slide represent some very common ADTs used, but there isn't like a set number of ADTs. You can't memorize all of the ADTs. Instead, you can sort of make bespoke ADTs for whatever you want. Say I, an instructor, am making an ADT to represent a course that I'm teaching. Maybe I tried out those awful new Aurora updates, and I think I can do better. Bet all of you could do better. So I'm making some code with a data structure to represent courses. The first thing I would consider is the data that you need to put in the structure. So I would consider every student enrolled in the course who has it. And each student has a name, student number, student ID, email, grades. That would be in something like a class or a struct representing a student. And then the course also has some more data, assessments, grading scheme, a size, which is just the number of students. So that's all the data, the things, the objects. And the other essential part of an ADT is the set of actions you could take, the operations you can perform on that data. So that could include enrolling or unenrolling a student, looking up the student's grade on an assessment, calculating a student's grade in the course, getting the size of class, calculating the class average on an assessment. You could probably think of some more. What's important here is that we have data and actions. Lots of different ways you could think about this. I already mentioned the math metaphor with the data being a set and actions being operations in some sort of abstract algebra construct. If you're more into language, you could say that an abstract data type consists of several nouns and several verbs that act on those nouns. Like I said, lots of different ways to think about this. No one way of thinking about this is guaranteed to make sense to you immediately, but I'm sure that one of them will eventually. This apparently is Jennifer Vaughn's cat, Kit Kat. I decided to leave this slide completely unchanged because I thought it was adorable. And like, my last name's Kit. So this is the Kit Kat in this context. Anywho, we're doing some operations on Kit Kat, who is enrolled in my course. And you can write code to use your ADT. In this case, we're calling the class for our ADT Comp 2140. That doesn't look very generalizable. A software engineering TA might complain about that, but let's just move on from that. So this Comp 2140 object is an implementation of our ADT. That'll become more meaningful later. And then the class student instance KitKat is just, or it is also a class, and it's part of the ADT, but it's not the ADT itself. The actions, operations, the verbs, whatever you want to call them, in this case, are implemented using methods. So using the enroll method on the Comp 2140 class is our implementation of using the enroll operation on the Comp 2140 ADT. And then this is just more method calling, more operation using. We use get assessment grade, get overall grade, get average score. Cool. So from the code, you can get a general idea of what the class does, but you have no idea how it works. The students are surely stored somehow, but you don't know whether it's stored in like an array, linked list, some esoteric data structure that you'll hear about in passing during fourth year and then never use. So the way the data is stored is kind of opaque. What we'll get to soon is that that's a good thing. Likewise, the algorithm used for the operations are not obvious at all. If you search for a student, like what search algorithm are you using? The fact that you don't even know the data structure used to store the students makes it really hard to even guess. If you want to sort them, if they even are sorted, how are they sorted? So this brings us to why we're using ADTs. Like, why introduce that weird concept in between the stuff that you're trying to implement and its implementation? Why not just say, throw the students in an array? It's going to be an array of students. Everyone knows about this. This is sort of a lesson you'll learn over and over, and it's that information hiding is pretty important in programming. I'm just going to look ahead and see if there's a slide that explains it. If it doesn't come up for a couple slides, I'm just going to talk about it now. Okay, this one's important, so I'm going to save it. The ADT's operations are sort of like a contract that says what you're allowed to do or what you're not allowed to do with the data. So even if you have, like, if you're using the ADT that someone else has implemented, the ADT gives you a set of operations and a guarantee of what will happen with those operations when they're executed. So unenroll, for instance, will just unenroll one student without affecting any others. Likewise, the user agrees to use only the operations supplied by the interface. So like, if you figure out how the data is stored, you won't interface with it directly. You'll still only use the methods given by the class, the operations given by the ADT, to retrieve data, in this case, student records. Okay, here's the big one. The reason we care about information hiding so much is because it turns out to make collaboration way easier. Whether it's collaboration between two coworkers on a project or like someone making a big open source library and then someone across the world who they've never met using it. If the implementation details, such as the data structures used and how exactly the code works in the operations, or if this implementation detail is hidden, then it can change. The developer behind the ADT can change how the ADT is implemented without affecting anyone else's code, the code of anyone else who is using the ADT. So say my Aurora SQL has gotten amazing success. Everyone uses it now. Universities across the world or whatever. And I'm storing students' records in a sorted array. But I realize that makes the enroll and unenroll operations a bit awkward for reasons that you'll learn about later in this course. I realize that I could use a much better data structure than a sorted array, better for this case at least. I could use a hash table. So if all the university's developers who are using my Aurora SQL ADT were told this thing sorts students' records in a sorted array, and I decided to change it to use a hash table, that would wreak havoc. Everyone using this code would have to rewrite their code to use the hash table instead of the sorted array. Or, I guess, they could choose not to update and then miss out on any new features or perhaps security updates. That would be messy. Instead, if I develop this the quote-unquote right way, there are very few things that have for sure right or wrong answers in computer science, but information hiding is generally a very good idea. If I did this the right way, my course thing would be an ADT. None of the other developers using it would know that I used a sorted array. They would just be using the enroll and unenroll methods without accessing the data structure. I could just swap out the data structures, rewrite the enroll and unenroll operations, or the methods, and then ship out the new version. The interface would be unchanged, where the interface is how the other coders use the code. So the changes that I made to my code don't require people using my code to make changes to their code to accommodate me. That's the big idea of this. And if you're also among the last students taking Comp 2160, you'll learn about this in that class too. And also, frankly, you're going to learn about this idea again and again because it's a very helpful idea. You'll go much deeper into it in the software engineering course. So going a bit more practical again, when we're doing actual coding for assignments, we're going to use Java, of course. And different languages have different features or constructs or ways to implement information hiding. The way you do it in C is kind of wacky. Again, you'll learn about that in Comp 2160. In this course, in Java, we're going to use interfaces to represent ADTs. As you hopefully learned in Comp 1020 or 1010, an interface just provides a list of method signatures. A class can then implement that interface and then define all of these methods. And then by the wonderful worlds of polymorphism and object orientation, you could write other operations that just take an instance of that interface and then any class that implements that interface can be used in its place. In this case, we've generalized that Comp2140 example a little bit to turn it into CompSci course. CompSci courses are ADT. We have operations enroll, unenroll, among others. And the ADT is like the idea. The beginnings of our implementation in the code is using this interface. So like I said, this represents the operations. The way you represent the ADT's data is just with other classes, or maybe they're structs. I don't really care. Maybe they're primitive types, like ints or floats. Just organize it in whatever way makes the most sense for whatever you're trying to accomplish. When you implement the interface, you can, you have to define all of the methods that you're given the signatures for. And in that case, you can implement any policies or any logic specific to your data structure. In this case, Comp2140 implementing CompSci course would include any logic that's like specific to this class and its syllabus. I think this example is kind of straying away from what an ADT is, but whatever. We have to talk about like the practical stuff, the language specific stuff eventually, or else you won't know how to actually code anything. So we talked about that first bullet point already. I want to really drive home the point that like ADTs, I don't want to say they don't exist in your code at all, because they kind of do. It's in that interface we saw earlier. But in general, an ADT is just an idea. It's like a mathematical construct for what data you have and what operations are can act on it. The ADT is the idea, and then the implementation of the ADT is the code that you write to actually turn it into a real thing. When you implement an ADT, you choose a specific data structure and write specific algorithms to carry out that ADT's operations. I want to talk about this more, but I'm pretty sure there's an example coming up that's more applicable to how ADTs and their implementations are actually used. I think that Comp2140 thing was a bit contrived. A good rule of thumb is that the stuff that an ADT, or that is in the ADT, is the stuff that the users of it know about, what data is stored and what they could do with that data. And the implementation of it is all of the choices that the user doesn't see, the stuff that they don't care about, the stuff that they shouldn't have to care about, because if you change it, they shouldn't have to change their code to adapt to it. So it's all the behind the scenes stuff. This last bullet point isn't the example I was thinking of exactly, but it is a very good example. Stack is an ADT. If you haven't heard about stacks yet, we're going to talk about them a lot soon. But it basically lets you access data in an order similar to a stack of papers or plates. The last thing that you put on the stack is the first thing that you take out. Call it last in, first out order. I don't want to go too deep into it yet. Just know for now that the stack is a specific way, or it's an ADT that gives you a specific way of accessing data that's useful in many cases. All there is to a stack is the fact that that data is accessed last in, first out. I didn't tell you anything about what code or algorithms are used to make a stack in code. It can be implemented using an array or linked list or probably many other data structures. It's the implementer's job to pick the data structure. Whoever's writing code that uses the ADT doesn't care and shouldn't be able to tell. If you want to tell whether something counts as an ADT or whether it's a data structure, the rule of thumb that I talked about earlier is that with an ADT, there would be multiple different ways to implement it. So with this example, you may or may not have heard about graphs. I think most of you have because of Math 1240. If you want to write programs that use graphs, you have different data structures to implement them. We're going to look at those later in the course, actually. But for now, you can use a thing called an adjacency matrix or an adjacency list. They're sort of analogous to arrays and linked lists, respectively. So you have multiple ways to implement a graph, so it's an ADT. Likewise, a tree, you can implement it using a linked data structure where each node of the tree has references to its children, maybe its parents. Or you could use an array and make it so for a node at a given index, its children are at specific other indices that you get by doing some operation on the index. So again, you have an idea what a tree is from Math 1240, and if you don't, we'll talk about it later in the course. And there are multiple things in code you can do to actually turn that idea into a program you can run. The latter two examples are actually data structures, not ADTs. An array is just a sequence of data of the same type that is organized contiguously, so every object is next to the others, contiguously in memory. That is the definition of an array. You can't implement an array using a linked list because while they're both ways of storing sequential data, if you use a linked list, that's not an array anymore. Since these earlier examples were about what the idea behind, like generally how the data is organized, these are ideas, and an array is more strictly about how the program works. An array is a data structure. Likewise, or just like arrays, linked lists are specific data structures. They consist of a piece of data and a pointer to the next piece of data. While there are multiple variations on linked lists, which we'll talk about later this week, later this lecture if we're going fast. While there are many variations on linked lists. There aren't multiple ways you can make the same linked list. A linked list is just a linked list. Right, here's an example that's more grounded in what we do in this course. This ADT is hella useful. Back when I cared about getting co-op jobs and would grind LEET code questions, a huge amount of them, or a huge amount of my solutions to them, started with, oh, you should probably store the data in a table. In my case, I was using Python, so they were called dictionaries, but it's the same idea. In a table, each entry has a unique key, and entries are accessed by their keys. So for instance, you could be storing student records, so the entries would be students, and their keys would be their student numbers. A table doesn't have a specific size. It can change dynamically as entries are added or removed. The list at the bottom of the slide is a bunch of operations you might want to perform on a table. It's not exhaustive. There's not one single exact true definition of the table, but it's an idea that you'll find implemented in a lot of ways in a lot of different cases. And generally, when you have a table, you can create a new empty table, get the number of entries in the table, add a new entry, get the entry with a given key, delete the entry with a given key, print the table, or empty the table. So let's say assignment 3 comes along, and one of the questions is implement a table. Write code that does the stuff I talked about here. Well, unfortunately in this course, you can't just go to the Java standard library and search up table and use their implementation of a table. The goal here is to give you a really thorough understanding of it, and to do that, you have to do it yourself. So what data structure should you use? I can certainly see this being implemented using an array. You would implement getting the entries just using array indexing. But you could maybe use a linked list as well. Getting entries would be kind of awkward, but you wouldn't have to worry about resizing it as you would with an array, since arrays are fixed size. So I think this is finally the first instance of one of the major themes of the course, which is that there's no one correct data structure for anything. Data structures have different trade-offs and advantages and disadvantages, and it's up to you to choose data structures that will give you advantages that are relevant to what you're trying to do and disadvantages that don't really matter. And of course, you'll get that intuition for how to choose data structures by actually making them yourself. Whew. The main operations we're going to care about in this example are insert, search, and delete. So I recommend keeping the student example in mind throughout the example. So insert would be enrolling a student in the course. Search would be getting a student by their student number, and delete would be making them drop the course. It says exercise for the reader, but we're going to talk about it still. Suppose we've decided to implement the table using an array. There are a few things we need to think about, some design decisions that we have to make. Also, by the way, quiz and especially exam questions on this topic will very likely involve you making these design decisions and justifying them with a couple sentences. So be prepared to think really hard about that. Would you store the entries in sorted or unsorted order? What algorithms would you use to use insert, search, and delete? And then, oh yeah, asymptotic notation is going to come in handy as an easy way to compare different algorithms, but we'll get to that. And what are some advantages and disadvantages to the array implementation? Pretty sure it elaborates in later slides. Ah, dang. So the sorted versus unsorted question depends on how you're implementing insert, or no, search, actually. If you're just doing search by student number, or like by array indexing, then it doesn't really, or it kind of forces you to sort them. Like student number 7865458, that's me, would be stored in array index 7865458. That's probably a really bad implementation. We'll give you a humongous array where most of the entries, like before 7 million or so, 700,000, whatever number it is, are empty. But yeah, I guess that's a valid implementation. Another thing you could do only if the entries are sorted is to use binary search, which, as you know, only works on sorted data. So sorting the entries lets you, or it gives you more options for what algorithms to use for searching. And probably deletion as well, because the delete algorithm will probably be sort or search for the thing you're trying to delete and then delete it. So sorting gives you more options, but it also involves some overhead. It makes the insert operation a lot more difficult, especially if you're using an array, like in this example. Inserting into the middle of a sorted array would require you to shift every other element to the side, which could be very slow and inefficient. So you have to decide whether you prefer efficient searches with sorting and fast searches and slow inserts if it's sorted, or fast inserts and slow searches with unsorted. Because if it's not sorted, you could just plop new entries to the end of the list, and then search, you'd be forced to just use linear search, loop through the entire array and check each entry. So to decide whether you would store entries in sorted versus unsorted order, you would have to consider which operations are more important for you. In this case, because we're imagining a data structure that handles student data, I think I would use the search operation way more frequently than insert, because I would want to do things like enter grades more often than people joining the course, which only happens in the first 2 weeks. So thought processes like these happen very often in the real world, where you have some goal that you want your code to accomplish, and some pros and cons to different ways you could go about accomplishing that. So I've already talked a bit about insert and search. Delete is just searching and then moving stuff over. And these would generally take linear time-ish. I think that's a decent thing to elaborate on. Insert in a unsorted list is just adding a new element to the end, and that takes the same amount of time no matter how many things you have in your table. So that would be constant time. For a sorted list, you would have to find the right place to put it in and then insert it. So inserting would depend on the time complexity of your searching algorithm, probably linear time.